So how on earth can this be true? We have the area here of a sector, not a triangle, but yet we have the same formula, base times height divided by 2. Now, it's a different height, it's a different base, but still the same formula. That seems very surprising. Let's look at how this can work, and let's start by defining what even a sector is. So, in our circle, this bit in orange is called our sector. It's actually the exact same shape that we have over here. The way our sector is defined is it goes through the centre of our circle, and then it has a length, which is the radius. Now, in this case, the radius is the same as our height, and it also has an arc length. This is called an arc. And actually what you can see is that's just a part of the circumference of the circle. We also have this over here. This is the angle, which we're going to call theta. That is the angle that defines how big our sector is, because you can imagine if theta was bigger, we'd have an even bigger sector there. Now, we actually already have a formula for finding out the area of this sector, and that formula is this. The area of a sector is theta divided by 360 times, you might recognise this bit, this is just pi r squared. This is just my general formula for finding the area of a circle. So what's this extra bit? Well, that just tells us what proportion of the circle we're looking at. For example, if we had 90 over 360 times pi r squared, that would be a quarter of a circle. We'd be dealing with just a 90-degree angle there, because it's 90 degrees out of the whole 360. Let's look at an example a bit more visually. So we have this GeoGebra, and I'll link it below, because I didn't make it, so I'll link it below. What we can see is we have this sector, and as I change the angle, the size of that sector changes. Similarly, as I change the radius, the area of that sector will change. What we can see is our formula in action. Theta divided by 360 times pi r squared. And in this case, theta is 102 times pi r squared gives me an area of that sector of 4.31 units squared. See, as the angle changes, the proportion of the circle we're looking at changes, and so the area in question changes each time. But this formula doesn't look like base times height divided by 2. In fact, in our formula, we have no mention of theta at all, which is what's cool about it. So let's just make it a bit smaller so we have some space. Now, we've introduced another formula here, and that is this one. And that is the formula for finding the length of an arc, this arc length here, otherwise known as the base of my upside down sector here. And it looks very familiar to the one above. It's just a proportion, depending on the size of that angle, times this formula, 2 pi r, which you might remember is just the circumference. So basically, to find the length of an arc, it's just what proportion of the whole circumference are we looking for. So now we have these two pieces of information, that's actually all we need, because we can see our formula doesn't have a theta in. So what we're going to do is we're going to use these two formulas that do involve theta to remove the theta to find our base times height divided by 2, our surprising formula. Let's start by writing like this. The area of a sector is equal to theta over 360 times by pi r squared. Similarly, the length of the arc, let's use little a there, is theta over 360 times by 2 pi r. Now, we want to find a formula for the area, but we want to remove the theta. So what we're going to do is rearrange so that we can eliminate this term here, So we're going to rearrange our second formula. So we have a equals theta over 360 times 2 pi r. We're going to rearrange for theta over 360. So we're going to divide by 2 pi r. So we've got that theta over 360 is equal to a over 2 pi r. A over 2 pi r, where a is that arc length, or that base of my funky triangle at the bottom there. And now we're going to sub this in to formula 2. Remember, formula 2 was just area equals theta over 360 times pi r squared. But now we're going to substitute this into theta over 360. So we have that my area is in fact a over 2 pi r multiplied by pi r squared, which is a pi r squared over 2 pi r. Can you see what cancels? Well, we can divide the top and bottom by pi, and actually we can divide the top and bottom by r. So we get rid of an r here, this becomes just r, and we get our formula. The area of that sector is just a times r over 2, where a, that arc length, is the base, and r over here is the radius, is the height. So there's our formula. A times r over 2, base times height divided by 2. How surprising is that? So we can actually use this formula to answer lots of questions that look like this. For example, let's say I had a sector that looked like this, where this was 8 and this was 3. We now don't need to know what angle theta is. It's irrelevant. We can just do a, the arc length, or the base, times r, which is the radius, over 2, which is 8 times 3 over 2, which is just 12. So the area is just going to be 12 units squared, which is pretty neat. So let's look at another question. We've got this sector. Now, while this might not look like our triangle, I can just rotate it. And now we have the same sort of shape. We have our base, we have our height, which remember is just the arc length and the radius. We use our formula. Area equals a times r over 2. So the area is just 10 times 6 over 2, which is 30. And there we go. What a nice and surprising formula. So next time someone says that the area of a sector is theta over 360 times pi r squared, you can just say, no, it's just base times height divided by 2. Thank you so much for listening. See you in the next one.